With some delay, we are ready to welcome our plenary speaker, who is Professor Antonio Visioli from the University of Brescia. Antonio was born in Parma and where he graduated in 1995, and then he got a PhD in the University of Brescia. And now he holds a full professorship in automatic control at the same university. And he is one of the most renowned experts in the field of applied control, mechatronics, and industrial control. He is a senior member of IEEE, Institute of Electrical and Electronic Engineers, and he also serves as chair of a technical committee on control education of the International Federation of Automatic Control. He also published several books as an editor and also as a leading writer, both textbooks and research books. And his other interests are in anesthesia control, which is also the main topic of this keynote lecture. So we're now ready to start and welcome Antonio to this stage. Please.
Thank you very much for the presentation. Maybe I do not deserve to be a keynote speaker after the very interesting presentations of yesterday and today. And thank you very much for the invitation to Andrea, Laura, and Alessandro. It's very interesting workshop, and I'm very happy to be here. So I try to make this presentation interesting, and I hope it will be at the end. So the topic, as Alessandro said, is closed-loop control of anesthesia. We have worked in this topic for a few years. And I would like to underline a help for the anesthesiologist. So we have to take into account that the application of this control strategy has to be supervised by an anesthesiologist. Okay, so I will start with a joke that my friend Margaret Bauer made a few weeks ago. Okay, and it says why process control engineers should not be doctors. We have managed to stabilize the patient. Okay. And I partially agree with her. Okay, it is true that the process control engineers should not be doctors, but they should cooperate with doctors. Okay, so the cooperation between control engineers and medical doctors, in this case anesthesiologists, can give nice results. And the idea is indeed to stabilize the patient at the right set point. Okay, that's very important, the right set point. Okay, so. Of course, we are a research team, okay, with many people. I would like just to underline the presence of Fabrizio, who has just presented his talk. But most of all, we are cooperating with Professor Nicola Tronico. He's the head of the anesthesiology ward in the Brescia hospital, and Massimiliano Paltenghi, who is the anesthesiologist who goes to the operating room. Okay. And so thanks to them, we have been able to have, let's say, interesting results. Okay, so this is the outline. Okay, I will go quite fast. I will spend a couple of minutes saying what is anesthesia. Okay, the general idea is that while the surgeon cuts, you have to sleep and you do not have to feel pain. Okay, let's say a little bit better. Anesthesia consists of three main components. The first one is hypnosis. And so you have to sleep at the right level, depth of hypnosis. And usually hypnosis is induced through a drug called propofol. Then you do not have to feel pain. This is analgesia. In order to avoid this, you have to use a specific drug that is usually this drug is called remifentanil, and this acts as analgesics. And then in some surgery procedures, you have to achieve also neuromuscular blockade, and this is usually achieved by means of a drug that is the Curar. Okay. So The idea is that the anesthesiologist has to induce these, let's say, 2 or 3 drugs in order to have to stabilize, let's say, the patient when he or she undergoes a surgical procedure. Okay. Let's focus just a few seconds on neuromuscular blockade. The idea again is that the patient should not move during surgery, and this is achieved by administrating Curar. The neuromuscular blockade has been extensively studied in the literature. There are well-defined and clinically accepted measurement techniques. The most common one is called the train of 4. And the main issue is that there is no interaction with other component of anesthesia. So the control of neuromuscular blockade can be handled by itself, and for this reason we are not dealing with this in this talk. Okay, let's say it is quite simple, and it is not always used in surgical procedures. Actually, in our surgical procedures we do not use Curar. Okay, so let's focus on hypnosis and analgesia. As I said before, hypnosis is the loss of consciousness, and it is induced through the propofol, while analgesia is the absence of pain, and it is induced through remifentanil. Of course, hypnosis is not enough because it is necessary that the patient does not feel pain, and because this can be stressful for the patient. Why hypnosis and analgesia should be considered together and not separately? Because propofol and remifentanil have a strong interaction between them. First issue. So we have a multiple input control problem where there is coupling between the effects of the 2 drugs. The second issue is that actually currently there is no reliable measure of pain. We have not a sensor that is clinically accepted in order to measure the level of pain. While on the other side, we have a measure of the depth of hypnosis, as we will see in a few seconds. So this has to be avoided, of course. During the surgery, there should not be awareness. So the patient should sleep constantly, let's say, during the surgery, because if there are episodes of awareness, this can be very traumatic for the patient, as it is, let's say, quite obvious. In clinical practice, there is an anesthesiologist that performs manual control with the patient. How does the anesthesiologist work? First of all, the infusion rates of hypnotic and analgesic, okay, depends on the experience of the anesthesiologist. That's, of course, very important. And when we have to design a control system, we have to exploit the experience of the anesthesiologist. This is why we have frequent talks with them. Then, of course, the knowledge of the surgical procedure. This is quite difficult to implement in a control system because it has to be known in advance. Then the anesthesiologist look at non-measurable physiological signs like facial grimacing, lacrimation, diaphoresis, frequent urination, and so on. And there are other measurable physiological signs like blood pressure, so hemodynamic, let's say, measurements, blood pressure, heart rate, saturation, and so on. The most important, let's say, that is our process variable is the so-called processed electroencephalogram, which allow us to measure, to have an indirect measure, let's say better, of the depth of hypnosis. And so this is really very important to have a feedback control system. But also the anesthesiologist in manual control look at this number, let's say, and decides the administration, the infusion rate of the 2 drugs. And then, of course, the anesthesiologist also relies on model-based standard procedure. So they know that for a given patient, for a given surgical procedure, for a given problem, they have to act in some way. And this means that they have a model-based procedure. Okay. So, as I said before, it is important to have a measure of the depth of hypnosis, and this is achieved in our case in Brescia, but also largely in Europe, through a so-called processed EEG, and this is called the bispectral index scale, or simply BIS. So the BIS is a number from 0 to 100. Let's say better from 100 to 0. 100 means that the patient is fully awake. So maybe if you measure the BIS of myself or of you now, it's 98, 100, and so on. And then it goes to 0, and 0 means that your brain, let's say, is flat. Okay, your electroencephalogram is flat. And you have, of course, an integer number from 100 to 0. During surgeries, the target value of the BIS is 50. That means that you have between a deep and moderate hypnosis. So this is our set point for the control system. Actually, we can say that any value in the range between 40 and 60 is acceptable. So our control specification is to infuse the right amount of propofol and remifentanil in order to keep the BIS between 40 and 60 through the surgical procedure. One main issue of the BIS is the presence of a high level noise. And here you can see this is the blue line is the BIS value for a given surgical procedure and for a given patient. The red line is the signal quality index, but you can see that there is a large amount of noise. And of course, for the feedback control system, this means that you need some filtering. Okay. So summarizing, in the standard clinical practice, the feedback loop is this one, and we are in manual control. The anesthesiologist look at the value of the BIS. Of course, the anesthesiologist also looks at other hemodynamic variables and unmeasurable signs of the patient and decides the infusion rate of propofol and remifentanil. So why do we want to change this situation? Because, of course, there are many surgical procedures, around 4.5 million in Italy each year. I think that in Brescia each year there are about 40,000 surgical procedures just in the Brescia hospital, okay, in 1 year. And there might be problems caused by underdosing or overdosing. For example, one of the problems of overdosing is the so-called PONV, postoperative nausea and vomiting. And of course, the use of a large amount of drug may cause a longer recovery for the patient, which means that the patient, of course, has some discomfort, and it means also that the costs for the national health system increase. And the effect of underdosing can be, again, anesthesia awareness that can be very traumatic for the patient. It can cause nightmares also after some years after the surgery. So we need to optimize the infusion rates, and for this purpose, we propose this, let's say, obvious solution, that is to have an automatic control system where it is a controller, an automatic controller, that based on the value of the BIS decides the amount of propofol and remifentanil to be administered to the patient. As I said before, this should be a help for the anesthesiologist. It's not going to replace the anesthesiologist. So the anesthesiologist should act as a supervisor. But the idea is that the anesthesiologist is very happy to have an automatic control system, because in this way, the anesthesiologist can focus on other tasks and they have their hands free. Okay, so it's like an automatic control system for an airplane. Okay. So what are the objectives of an automatic control system? Decrease the workload of an anesthesiologist. If the surgery procedure lasts 10 hours, for example, of course, there can be problems caused by distraction or fatigue of the anesthesiologist itself. We want to achieve a better anesthetic level, less drug administration. Let's say better, the right amount of drug administration, okay, so to avoid overdosing, which yields a better postoperative recovery and reduction of side effects. So overall, an increase the safety for the patient and a better work for the anesthesiologist. Actually, the anesthesia procedure consists of 3 phases. 2 of them are relevant from a control point of view. The first one is the induction phase. The patient is awake and has to sleep as soon as possible. So from a control engineering point of view, this is a set point following problem. And we have that the depth of hypnosis, let's say the value of the BIS, should be brought from the starting value of around 100 to the target level of the target set point value of 50. So this is a set point following problem. And this has to achieve as soon as possible, less than 5 minutes to avoid the discomfort for the patient. If I undergo to a surgical procedure, I want to sleep as fast as possible. I don't want to be awake while they are doing something around me, okay? And of course, this also means a fast set point setting time means that the surgical procedure lasts less, okay? But during the set point following task, you have to go, to the value of 50 as soon as possible, but without too much undershoot, because a too low value of the BIS might cause some hypotension and some problems after the surgery related to delirium. Okay, this is what the medical doctors say. The second phase of the anesthesia, so once the patient has a BIS value of 50 or around 50, we start with the maintenance phase. That is when the surgical procedure actually has effect, so there are noxious stimuli. In this case, the BIS has to be maintained to the value of 50, or let's say better from 40 to 60, despite the occurrence of disturbances. And from a control engineering point of view, this is a disturbance rejection problem, okay? In order to simulate a disturbance, we just apply a step signal to the BIS signal, okay? Very simple. Actually, disturbances have different shape, but the idea is that if the control system works well when a step disturbance occurs, it will work well also with other kind of disturbances. Okay, so we have the disturbance here, and remember we have the noise on the BIS signal here. Of course, we need also to consider saturations of the pumps, because the pumps have saturation limits and also slew rate limits. Most of all, they have saturation limit. Obviously, the lowest value of the saturation limit is 0. We cannot remove the drug from the patient. So if you have an overdosing interval, this can be a problem, okay? So just to stress better, what are the control requirements? Of course, we want to limit, we want to take into account the limits of the actuator, and I will come back to this issue later on. We want to avoid those unnecessary variations of the control action. What does it mean? It means that the control action has to be supervised by the anesthesiologist, so has to be understood by the anesthesiologist. If there is an increment or a decrement of the control action that doesn't make sense, let's say because of the noise, then the anesthesiologist may not trust the control algorithm, okay? And these are the requirements related to the process variable, the control variable. So as I said before, fast set point tracking, no more than 4 or 5 minutes. Bounded undershoot of BIS during the induction phase. The BIS level should not go below 40 in principle. Fast disturbance rejection, BIS between 40 and 60 during the whole maintenance phase. Most of all, the main issue in such a kind of application is robustness. Because of course, we want to use the same controller for a large variety of patients. And it is obvious that a patient that is old, very tall, with a large weight, and so on, will behave different from a patient that is young, healthy, thin, and so on. Okay, so we have large variety of patients, and this means that we need to be robust to interpatient variability, but also the same patient along the surgery procedure might change his or her dynamics, and this is called robustness to intrapatient variability, for example, because of the loss of blood. How did we design our control system? the principle, the main idea is quite simple. We choose a specific kind of controller. We will see a PID controller, the most obvious option, okay? Then we selected a set of patients, 13 patients, okay? I will go into details later on, but 13 patients, which according to us, and according to the literature, to be honest, are representative of a wide population. So we say, okay, if our controller works well with these 13 patients, it will work well for the whole population. We are talking about adults and not children, of course. So we decided to tune our PID controller with an evolutionary algorithm, genetic algorithm, particularly because swarm optimization, they behave the same. Of course, we cannot say, okay, that's the end, because we have to test actually the robustness of our controller on a wide population. And for this purpose, we used a Monte Carlo method. So the idea is quite simple. Select a simple controller, tune it by using an evolutionary algorithm on a reduced set of patients, test if it works on a wide set of patients. In order to simulate the patient, we had to exploit a so-called PK/PD model of the patient, pharmacokinetic pharmacodynamic model. Pharmacokinetic is the dynamic of drug concentration in the human body. Pharmacodynamic is the relationship between drug concentration and clinical effect, the BIS. I will go quite fast because you know very well how to model such a kind of systems. Of course, we relied on the literature. There are well-known PK/PD model for propofol and remifentanil. There are actually 3 compartments model for the PK part, and the PK part is linear for both propofol and remifentanil. Okay, this is the propofol model. So we have actually a simple third-order system. Regarding the pharmacodynamics, we have a first-order linear system, this one, okay, quite simple, followed by a nonlinear Hill function. So we have actually a Wiener model with a linear part and a nonlinear, a static nonlinearity. Actually, we have that the parameters of the model of the linear part depends on the demographics of the patient, so gender, age, weight, height. But the nonlinear part is unknown. So the parameters on the Hill function, C, E, 50, and gamma are unknown. The only thing we can do is to use average values, but there is a large uncertainty on the nonlinear part, which makes the control problem, let's say, quite difficult to solve. There is actually uncertainty, of course, on the linear part here, but it is slightly less relevant, okay? So this is for propofol, okay? So as I said before, the most important role is played by the Hill function, and of course gamma denotes the steepness of the function, okay? And C50 is this point here. Okay, if we combine propofol and remifentanil, for remifentanil we can do the same reasoning, but then the Hill function is actually this one here, so it is a 3D surface, okay, but we can do more or less the same reasoning as before. So we have a static nonlinearity that is described in this way. So as I said before, we wanted to design our algorithm based on a reduced set of patients, and in the literature we found these 13 patients. Actually, the 13th one is the average of the first 12. There is a mistake here. This should be 11, sorry. And so we said, okay, if our controller works well with these 13 patients, it will work well for all the patients. And so we used a genetic algorithm to tune a PID controller. Now, the main problem is that actually, as I said before, the system we want to control, the patient, okay, is this one, the patient is this one, has 2 inputs, propofol infusion rate, remifentanil infusion rate, and 1 output, the BIS. So it's a multiple input, multiple output system in principle. Actually, is a multiple input, single output system. How can we deal with this coupling? Here, the key idea is to use just one PID controller and then to fix a ratio between the infusion rates of the two drugs. This is done according to the anesthesiologist, of course, that says, okay, if we fix the ratio, this is okay. In some standard practice, actually, the anesthesiologist keeps the remifentanil constant and they just change the propofol value. Of course, if there are some parts of the surgical procedure that are very painful, they will also increase the remifentanil infusion rate. But the general idea is to keep the remifentanil constant. Of course, they have just, let's say, two hands, and they have to control two pumps. It is much easier to leave one pump at a constant value and to control just one of them. So they said, okay, if we keep this ratio constant for at least some interval of the surgical procedure, this will have some benefit for the patients. And this also solves the problem for our control design of having two inputs, because the PID controller here sees a process that is this one, that is actually from the PID controller point of view, single input, single output here, okay? Of course, what is the right value of the ratio? Well, there is actually the remifentanil is in microgram per kilogram, while the propofol is in milligram per kilogram, and the ratio between the two is usually 2, but depending on the kind of surgical procedure, this ratio can change in a wide range. Okay, but if we leave the anesthesiologist to fix the ratio, we can change the PID controller settings according to the ratio chosen. So we can tune different sets of PID controller parameters depending on the ratio. And this is what we have done. So we select a standard PID controller, okay, with, of course, a strong, let's say, filtering action on the derivative action. And we solve this simple min-max optimization problem. The idea is to minimize the worst case integrated absolute error over the 13 patients. So we are safe that in the worst case, the integrated absolute error will yield a fast set point following response and also a fast low disturbance ejection response. Actually, since the two tasks are quite different, we have selected gain scheduling approach. So we have one set of parameters for the induction phase and another set of parameters for the maintenance phase. But this is quite simple in our automatic controller. So these are the results of the genetic algorithm for different values of the ratio. And we see that more or less the integral time constant and the derivative time constants are more or less constant, okay, depending on the ratio, while what it changes is the proportional gain here. So it is easy, let's say, to devise a tuning rule that depends on the ratio. So the anesthesiologist selects the ratio, and the value of Kp is updated accordingly, while the value of Ti and Td are the same for all the values of the ratio. We have a very slight loss of performance by keeping Ti and Td constants. And we see we have two sets for set point and disturbance tasks, that is for the induction and maintenance phases. As I said before, noise filtering, we have to strongly reduce the amount of noise. And for this purpose, we have used also such a kind of simple filtering, that is, we take the average value over 9 samples. Okay. These are simulations for the 13 patients, and this is the induction phase, and this is the maintenance phase. We see that for these 13 patients, we satisfy the clinical specifications. And we see red is the infusion rate of remifentanil, and which is in microgram, okay? And black is the infusion rate of propofol, which is in milligram. So, okay. Now, as we said, we have to test the robustness. So we generated in silico a large number of patients with different characteristics, age, weight, body mass index, and so on. And we see that for different values of the ratio, in any case, the induction phase satisfies the clinical requirements, as well as the maintenance phase. When we have a disturbance, it is compensated in the right way. Okay, and I forgot to mention that, of course, in the optimization problem, we took into account the actuator saturation limits. Okay. Now, the problem we have with this PID controller, okay, it works. We tested in the surgical, in the operating room, in surgical procedure, it works. But of course, the control action, even if we have filtered a lot the BIS, of course, we cannot filter too much in order to avoid too much phase lag. But the main issue is that the control action is quite noisy. So you see a lot of changes in the pump, and this is not, let's say, appreciated by the anesthesiologist. So we said, okay, let's move to event-based control. The idea is to mimic the way of doing of the anesthesiologist, and the anesthesiologist way of doing is, okay, if things are going well, I will not modify anything. When there is an event, I see that there might be awareness or overdosing, or the surgical procedure causes too much pain and so on, I will modify the control variable. Okay, that's quite easy. And this is what event-based control does. So the idea is to include in the control system an event generator, and when the event generator triggers an event, then we modify the control action. I will not go into details. We modify the PID controller in order to deal with events, and so we use the so-called PID plus controller. The PID plus controller is actually used by Emerson Process in chemical process control, okay, to deal with wireless sensors. But we exploited this idea of using a PID plus controller in order to introduce events and again to mimic the anesthesiologist behavior. In this way, the anesthesiologist is more happy, let's say, to supervise the overall control system. Okay, I will not go into much detail about the PID plus controller. What is more relevant is the event generator, and the idea is this one. We have that an event is generated when the integral between the current and the previous value of the BIS, the previous value when the last event occurred, is greater than a threshold. And then we send to the controller this value here, which is an average, let's say, of this value here. So the main idea is to filter the noise, because if we have random noise, okay, this will be filtered by the event procedure, the event generator procedure. This is an idea, of course, again, I go quite fast, but we have a noisy signal here, okay? The true signal is the thin line here, okay? The signal generated by the event generator is the thick solid line here. So we see we have a very good filtering of the noise. And in this way, we see that the control action is a piecewise constant control action, which is the typical one of the anesthesiologist. Okay, these are the events. Of course, when there is a disturbance, we have more events. When nothing happens, let's say like this, okay, we generate less events. For the purpose of safety, in any case, we generate an event every 30 seconds, okay, because we don't want to leave the patient without, let's say, any control or in open loop for a too long time interval. Okay, so we tested both procedure, the standard PID controller and the event-based PID controller in the operating room. And of course, we make we have the permission from the ethics committee of Brescia. Okay, and we have a simple controller with a graphical user interface. We have 2 syringe pumps and the monitor that give us the BIS signal. We have also available the hemodynamic signal, as I said, the blood pressure, heart rate, and so on. Okay, what is very important from the anesthesiologist point of view is the graphical user interface. Okay, this is a key role. nothing to do with the control system design, nothing that can be published in a paper, but this is the most important part of the control system for the anesthesiologist, because they want to supervise the system. Of course, they have the patient in charge, okay, so they need to have the situation very clear. And here we can see that this is the BIS signal. These are the propofol and remifentanil infusion rates. Here you can write some notes. You have some the possibility to add a bolus to the system, okay, to go to manual control when they want. Of course, they can detach the automatic controller and use manual control, and so on, okay. So these are some experimental results with the PID control scheme without events, and you can see that, okay, the transient in the induction phase is nice, and then the BIS level is almost all the time in the range between 40 and 60. So, of course, I picked up the best results, okay? Now, we have around 160 patients, okay? So, with both PID and event-based PID. This is another case where there is actually a slight overdosing here, but in any case, you can see the BIS level is between 40 and 60. But you can see that the control signal is very noisy, okay? So, and here, this blue line marks the change between one PID parameter and one PID and another PID for induction and for maintenance. As I said, we use a gain scheduling procedure. Okay, we have a comparison with manual control. I will go fast about this. Actually, the idea with the standard PID is to improve the performance by slightly modifying, but significantly modifying the control scheme. The idea is, in any case, for the induction phase to use a bolus, because this is a standard practice. As we can see here, actually, this resembles a bolus, but it is not actually the same bolus as the anesthesiologist would have done, okay, in clinical practice. So we prefer to keep the anesthesiologist into account and modify the induction by using a feed-forward action that applies a bolus to the patient as the anesthesiologist does. Okay, that's the important issue. But this bolus is calculated automatically based on the patient's data. And then the PID controller works to, of course, the feedback controller works to improve the performance in case the bolus is not the right one. Okay, let's say like this. And then we have also used baseline infusions administered when the predicted FXI concentration falls below a safety threshold. So the idea is to use a patient model. If we see that the predicted, of course, with some inaccuracy, FXI concentration falls below a safety threshold, then we apply a baseline infusion. Again, this is to mimic what the anesthesiologist does. With this PID controller, the infusion can be also 0 in some time intervals, which is correct from the feedback control point of view. But as the anesthesiologist is somewhat worried when they see that there is no drug infused administered to the patient. Okay, so we have applied these two issues. Sorry. And we see that in these cases here, you see, this is the baseline infusion. And this helps us to keep the BIS in the right range between 40 and 60. And at the beginning here, you have a bolus, which is, okay, has a short duration, but you see here we have the saturation level of the pumps. Okay. Okay. With event-based control scheme, we applied the same two modifications, okay, before going to the operating room. So again, we have the event generator, the PID plus controller, and the other two modifications. So the feed-forward action applied with the bolus and the baseline infusions. And this is the result with event-based controller, okay. So we can see that the performance maybe has slightly decreased although we are again in the range between 40 and 60, here you can see that the bolus at the beginning maybe has caused a slight overdoses, but it is recovered by the PID controller. You can see here that the control action switched to 0. Of course, we cannot again remove the drug from the patient. And let me also add that, okay, we have to be in the range between 40 and 60, but 40 is better than 60, okay, because we want to preserve awareness more than having a slight overdose of the patient. But the most important point we have to highlight here is that the control action is piecewise constant. So this is a control action that is recognized as good by the anesthesiologist, and that's important. Okay, if you remember the other one that was very noisy, this is really appreciated by the anesthesiologist. Okay, so as a conclusion, we can see that there are clear benefits deriving from the automatic control of anesthesia. Actually, even small improvements in the control scheme can potentially have a major economical impact. If we reduce the PONV episodes of 5%, which might mean that we reduce the recovery days in the hospital of 1 day for the 5% of the patient, it means a large amount of money, okay, but also, of course, an increased safety for the patient and a better recovery for the patient itself. And okay, stable anesthesia is beneficial for the patient. That's, let's say, quite obvious. I have pointed out here that in particular, it is also beneficial for the anesthesiologist. We have to keep this in mind. So our target, let's say, is obviously the patient, but we have to take into account also the anesthesiologist, because if the anesthesiologist does not accept the solution, then they will not use it. Okay, so this is why it is important to offer clinically appealing solution. Okay, that's the main issue. And of course, the Activa study is in progress. We have many things to do. We have tested model predictive control. We think that the PKPD models that are now available in the literature are not sufficiently accurate for the purpose of designing a model predictive controller. Okay, they are very good as pharmacological model, but they have been devised from a pharmacological point of view, not of course from a control design point of view. So we need to improve the model. And then we can also think about the inclusion of a pain sensor, which is really lacking in order to have multiple input, multiple output systems. So 2 drugs, 2 effects. Now we are just able to measure one of them. We would like to have also a reliable pain sensor. And then there are, of course, other issues that we are going to do in the next few years. Okay, I have put some references, but just for the purpose of, if I leave the slides to you, of course, you can look at the references. They are just our own references. Of course, there is a large literature also to anesthesia. We're not the only one who have worked in this field, but we are maybe proud of having clinical results because of this strong cooperation between us and the medical doctors. Okay, that's it. I hope I've been more or less on time. Okay, thanks for the attention.